We're here in Bagni de Lucca at the Laszlo Institute for New Paradigm Research. Over the past 2 days, we've been in a symposium titled the Infinite Consciousness Conference. And today, Stuart Hameroff has joined us and will be speaking to us a bit about the presentation that he's done here. And Stuart, so I've spoken to some of the other researchers and scientists who are here, and the general opinion is that you and your work are probably at the forefront of the material sciences research into consciousness. If you could define for us a bit about who you are, your background, and also what the central question that you're posing in your research is.
Well, thanks, Betsy. It's a pleasure to be here with you. I got interested in consciousness when I was an undergrad many, many years ago at the University of Pittsburgh in a philosophy of mind class. I was interested in physics. I went to medical school and was oriented towards brain stuff, neurology, psychiatry, neurosurgery, but eventually wound up in anesthesiology, partly to study how anesthesia works as a way to understand consciousness. But in medical school, I worked in a cancer lab and studied mitosis, how cells divide and how the chromosomes are pulled apart by structures called microtubules, mitotic spindles and centrioles that are made of these polymers of proteins, proteins called tubulin, that self-assemble and self-organize and organize everything inside cells, from neurons to simple cells, and seem to know what to do and where to go and organize things. And everybody else in the lab got interested in the genes and the chromosomes. It was the dawn of the genetic revolution, basically. But for some reason, I fixated on how these structures seem to have some intelligence, maybe even consciousness, at that level, organizing the chromosomes. Because if that wasn't perfect, you could have abnormal genotypes and then cancer, maldevelopment. So I got interested in microtubules. I was also studying computers, which are new to me. And I noticed that computer switching matrices, Boolean switching matrices, resembled microtubules, or microtubules resembled computer matrices. So I got the crazy idea that microtubules were processing information. That got me interested. That kind of set me on a trajectory that I'm still following, actually. I'm still obsessed with microtubules, which I think are the most interesting biological structures there are. But I wound up, as I said, going into anesthesiology. It suited my lifestyle better. It's fun being in the operating room. I enjoy it. And as the man who would be my future professor, Bernal Brown, said, if you want to understand consciousness, figure out how anesthesia works. So 40 some odd years later, I'm still an anesthesiologist and I'm still studying consciousness through microtubules. And fortuitously, it turns out that anesthesia actually acts on microtubules. So it's all kind of come together.
So when you were young, I mean, when you were a young man before you finished university, I mean, as a child, did you have a curiosity around consciousness, or did this come as you began to see how these mechanisms work?
My curiosity about consciousness happened in undergrad with a course in philosophy of mind, the science and physics I was taking, things that were going on in the 60s and so forth. But my academic intellectual curiosity started much earlier with my parents, but mostly my grandfather, who was a Russian immigrant intellectual who gave me books on Einstein and astronomy and the universe expanding and so forth, and really piqued my interest and in just science and academics in general. So I've always been curious. Consciousness came along during college as a topic, but once I got interested in that, it's kind of stuck with me. I'm still very curious about it. And among the other things I do, besides research, is organize and direct the Center for Consciousness Studies at the University of Arizona, where we host and organize conferences. We held the first international interdisciplinary conference on consciousness in 1994, Tour de Science of Consciousness. I was only going to do one of them, but there was a big demand and nobody else really wanted to do the integrative approach. So we've done it every other year since then in Tucson and odd-numbered years elsewhere around the world. So it's been going annually since 1994. We most recently had the 2016 conference in Tucson, and next year we'll be in Shanghai, China.
So the Laszlo Institute, Irvin as a Legacy project, is examining how to shift a paradigm in science to include consciousness.
Right.
Do you feel that science has the tools at this stage to actually define what consciousness is?
We're trying. I worked, let me back up and then I can answer that, because I think the answer is on the horizon now, or potential answer. So I spent about 20 years writing and studying and modeling microtubules as information processors, as computers. And then one day in the late 1980s, well, one of the points I was making was that if you go to the level of microtubules, there's all this information below the level of neurons. So artificial intelligence, computer people were saying, well, the brain's a computer of 100 billion neurons interacting at switches, which gives you 10 to the 16th operations per second, because you have 10 to the 11th times 1,000 synapses at about 100 hertz, 10 to the 16th. And the singularity, the AI people are started saying, we're saying back then and continue to say, when we get to 10 to the 16th operations per second in a computer, we'll have the equivalence of a brain, and we should have consciousness if we can program it properly and get the connections right. I think that's ridiculous. For one thing, if you look inside the neuron, you see all this processing going on. You can look at a single cell organism which doesn't have any connections, yet it swims around, it finds food, it finds a mate, it has sex, it can learn, it can do all kinds of clever things, and yet it's got no connections. It uses its structure, its microtubules basically. So if a single cell organism is that clever and its microtubules are that functional, wouldn't that be so in neurons? So I was going around being a pain in the rear end to these AI people saying, no, you got to consider all this deeper level processing. And so your goalpost is way, way downstream. It's not 10 to the 16th, it's more like 10 to the 27th, because that's what you get when you add the microtubule processing, theoretically. But then one day somebody said to me, okay, wise guy, let's say you're right. Let's say there's all this processing going on. How would that explain consciousness? How would that explain joy, love, feelings, emotion, maybe even spirituality? How would that explain feelings, consciousness? And this later became known as the hard problem, coined by David Chalmers, actually at our first Tucson conference in 1994. But other people had expressed it. Thomas Nagel, What Is It Like to Be a Bat, and many other people. Even William James had talked about the ineffability of the conscious experience as opposed to pure computation. Now, some people still to this day maintain that consciousness is computation, and that we have anything special like experience is an illusion. Daniel Dennett, for example. And a lot of people follow that. The AI people follow that because it makes their job simpler. I don't think that's right. So back in about the late 1980s, somebody asked me this question, and I was a little bit floored, because I hadn't really thought about that deeply, and I realized I'd become a reductionist, taking everything to a deeper level. But what's the point? You still have this ineffability of consciousness. How do you explain it? Well, fortunately, that same person, and I can't remember who it is, but I owe him a debt of gratitude, suggested I read a book by Sir Roger Penrose called The Emperor's New Mind, which I did. And Roger wrote Emperor's New Mind in 1989. I think I read it in about 1990.
We should actually explain to this audience who Sir Roger Penrose is.
Yeah, Roger Penrose is a mathematical physicist. He's currently at Oxford. He's been at Cambridge. He worked with Stephen Hawking on the original solution to Einstein's equations leading to singularities and black holes. Basically did the mathematics of black holes. He was Hawking's thesis advisor. They shared the Wolf Prize. He's also very well known for geometry, Penrose tilings, how you can tile a plane with non-repeating tiles, non-repeating patterns, and the structure of space-time geometry, whether it be spin networks, quantum geometry, twisters, all of these have sprung their own fields, and he really originated them. So he's probably the world's expert on the structure of the universe at the very nitty-gritty level, basically the Planck scale, and how it's organized, and has come up with one amazing idea after another. So he's a very eminent, very modest, but brilliant, and a very kind, sweet man. So I read this book, The Emperor's New Mind, and the title was kind of a snide commentary on artificial intelligence. And probably the emperor was Marvin Minsky, who was the scion of AI, and I think he passed away recently. But AI was saying, just give us enough money and we'll build a powerful enough computer. It'll be conscious. You can download your consciousness when your body gives out, and everybody be happy. Just give us another couple 100 million, and we'll take care of it for you. So Roger, so I had a beef with AI also, because not for a different reason. My beef was that they were considering one neuron and one synapse as one bit, and I thought, well, we have to go deeper and all this other information processing going on. But Roger attacked it from a more philosophical stance, coming from using Gödel's theorem, of which suggested that to understand something, you had to be outside the system. You needed to be outside. So you need something that was outside the computational system, or what he called non-computable. So the first half of the book was about Gödel's theorem. It was really hard to follow for me because there was a lot of jargon, a lot of philosophy I didn't understand. But I got the gist that he was attacking the premise that consciousness was a computation, that something else was needed. The second half of the book offered his solution for what that missing ingredient was, and it had to do with quantum physics. And that in and of itself was kind of a coup, because he dealt with the measurement problem in quantum mechanics. So our world, and I didn't know anything about quantum mechanics at the time, and I probably still don't know much. As Feynman said, anybody who claims to understand quantum mechanics is lying or crazy. But one of the things about quantum mechanics is that, well, you could see our world seems to be divided into two realms. In our everyday world, everything is definite in one place. Newton's laws, gravity, thermodynamics, electromagnetism work very well and make excellent predictions. However, when you get small, when you get and the size scale is uncertain, it can change. Things get different, and different laws take over. The laws of quantum mechanics. At the small scale, and again, we don't really know the cutoff. Particles can be in two places at the same time, quantum superposition. Particles which are separated by great distances can be connected by entanglement, EPR, quantum entanglement. So if two things are together, they go far apart. You make a measurement here, the other one instantaneously collapses to the opposite. Now, collapse means if you have a superposition of something in two states at once, it will apparently collapse to one or the other. So a quantum state reduction is sometimes called collapse of the wave function. So if you make a measurement over here, the other one instantaneously collapses to the opposite, complementary possibility. Einstein didn't like this because it implied faster than light, instantaneous meant faster than light signaling. And that violated his special relativity. But nonetheless, that turned out to be true. And in the 80s, so a prediction in quantum mechanics was that this would happen. Einstein didn't think it would, but in fact, he came up with the thought experiment, EPR, Einstein, Podolsky, Rosen, of making a measurement here and having this one over there. And, but in 1982, Alan Aspect in Paris did the experiment, and sure enough, you make a measurement here, the other one instantly collapses to the complementary. And that was just across the lab, but since then it's been done thousands of times at pretty significant distances, hundreds of miles, if not thousands of miles apart. So entanglement is true, superposition seems to be true, condensation or coherence, where particles condense into one object, so if you perturb any one part, all the particles react or feel it. So you have all these weird things going on at the quantum level. But we don't see these generally in our classical world. We see everything in one definite place, one at a time. And the reason we don't see this is called the measurement problem. Because it appears as if you make a measurement on a quantum system, the measurement itself causes it to collapse or reduce to one or the other. And in fact, that was one of the explanations that conscious observation causes collapse. And Niels Bohr, who was a pioneer of quantum mechanics, liked this because he could ignore the underlying reality and make his measurements, get a result, and go on and do experiments. And he was very successful. And quantum theory has developed one of the most successful branches of science there is. And all of our electronics, everything we have today is based on that. But Schrödinger saw a problem with this. He said, let's say you have a quantum system, like an electron in two places or opposite spins, and superposition of both, or a photon polarized in both, or some quantum system that has two possibilities. And let's say you amplify that. For example, you send the pair through a half-silvered mirror, and just by probability, one is going to be reflected, one's going to go through. Let's say the one that's reflected enters a box. In the box, you have a cat, and you have a vial of poison. And if the particle or a photon enters the box, it will trigger the poison and kill the cat. The other one will continue on its way. Schrodinger said, okay, if the conscious observer interpretation is correct, that would mean that if you do that, the cat would be both dead and alive until somebody opens the box and looks at the box, and only then would the cat be either dead or alive. And Schrodinger intended this as he called it, a burlesque example of how ludicrous was the conscious observer. And the possibility of quantum systems being amplified to macroscopic scales. So he did it as a way to show how silly it was, but the problem is we still don't have a good explanation for what happens. Now there are some other explanations like decoherence, that every quantum system will run into a classical environment and erode. The problem is at that level everything's quantum, and how could you ever have isolation? The other possibility is, another possibility that's been put forth is that that there is no collapse, that every superposition, every possibility, an electron spin up, spin down, each one will evolve its own universe. And in that universe, the spin up will go and everything else with it, and spin down will go over here. And we have and this keeps happening over and over and over again, so we have an infinite number of parallel universes. This is called the multiple worlds hypothesis, which despite being completely untestable, despite the ludicrousness, I guess, of having an infinite number of multiple worlds to solve this one silly little problem, although it's a tough problem, it's very popular. Physicists love it, the mathematics work, it allows them to ignore the underlying reality and say, well, there is no collapse, so let's not worry about it. You know, there's all these other worlds, who cares? So that's kind of the party line in physics, I think, along with artificial intelligence in computer science and neuroscience. Another possibility was put forth by Roger Penrose in this book in 1989 that I read, The Emperor's New Mind, the second half of the book. He proposed a new solution for the measurement problem that was new at that time. And that is that rather than having consciousness come in and cause collapse, collapse causes consciousness, or collapse is consciousness. But to do that, you need a mechanism and a reason for collapse to occur. And before attempting that, he took a step backwards and addressed what it could possibly mean for a particle to be in two places at the same time. I mean, everybody says, yeah, superposition is really weird, how do we get rid of it? But he said, well, let's go back. How does that actually even happen? And to do that, he solved yet another problem, at least to some extent. And that is the reconciliation of general relativity and quantum mechanics. So Einstein had put forth special relativity, which had the problem of precluding instantaneous or faster than light signaling, and also general relativity. And the key point in general relativity was that there is a space-time metric. There is some structure to the universe in which things propagate. For example, light can propagate. And that matter is equivalent to curvature in space-time geometry. So this was one of the key features of general relativity, that matter, mass, causes curvature in space-time geometry, or is curvature. So for example, he set up another experiment, which was later done, so it wasn't a thought experiment. He said, imagine there's a star behind the sun. Now we can't see it because it's behind the sun. But the sun is massive and will cause curvature in space-time. And first of all, he started with four-dimensional space-time geometry. Actually, Minkowski had that, so it's Minkowski-Einstein space-time geometry. And the star behind the sun would curve by the mass of the sun and be visible to us on Earth, even though it was behind the sun. So, I think it was 1929, Sir Arthur Eddington mounted an expedition to a mountaintop, and I forget where it was, but during an eclipse. So the sun was blotted out by the moon, I guess, and so you didn't have the brightness of the sun, so you could see anything that was kind of off its edge. And sure enough, and they calculated which star was going to be behind the sun, and sure enough, he was able to see the star due to the curvature of space-time around the sun, which was blocked out so that they could actually see. And this proved that space-time was curved. It proved that there was such a thing as space-time, as opposed, this debate had gone back to the Greeks, where was the universe a bunch of particles in a void, or was there some continuum or plenum, as the Greeks called it? And it went back and forth with the Michelson-Morley experiment, and then, which seemed to act against there being a structure. But then Einstein said, no, there must be, and this experiment proved it, that there was some kind of something or some entity, some structure to the universe, to space-time geometry, that could curve, and that matter could be considered equivalent. So Roger used this curvature idea, and in a brilliant and somewhat subtle way, he said, okay, that's for big things. Now imagine for little things. Let's say we have an electron, or let's say an atom here and an atom here, and each is going to have its own little curvature. But let's say it's one atom, and let's say it's oscillating back and forth between here and here. If it's here, it's going to have a little curvature this way. If it's here, it's going to have a little curvature this way. Now imagine that particle is in superposition. It's in both places at the same time. What you then have is a curvature over here and a curvature over here in the opposite direction. So it's kind of like the fabric of the universe kind of separates from itself, unravels, if you will, or shreds. And one will go this way and one will go that way. Now, it's in 4 dimensions. It's easier to think of this in 2 dimensions, but it's a separation in the structure of the universe. And if this separation were to continue, you would imagine you have multiple worlds. Each curvature, each branch of space-time would form its own universe, and you have a universe over here, universe over here. It happened again and again and again. You get an infinite number of universes. So Roger said, yes, superposition is a separation of the structure of the universe, as the multiple worlds suggested. However, and this is the key point, the separations would be unstable, so that they wouldn't continue to form their own universe. They would self-collapse after a time t, given by a very simple formula, the indeterminacy principle, which basically said the larger the mass, or the larger the curvature, the separation, the faster it would self-collapse to this one or that one. And then he added 2 key features. One is that when this happened, when this self-collapse occurred by the indeterminacy principle, there was a moment of subjective conscious experience. So rather than bringing consciousness in from the outside to cause collapse, which the conscious observer interpretation would suggest, which puts consciousness outside science, here you have the system itself, the universe, the superposition, causing consciousness or being equivalent to consciousness as an identity. And so there would be a little bing, if you will, of subjective experience. Now, this would be happening everywhere in the table, for example, but these little bings, or little moments of subjective experience, would be kind of random, disconnected, not entangled, not coherent, and they might be associated with feelings. It might be good, bad, otherwise, and so forth. But they would kind of cancel out, and there would never be any net movement, so the table stays where it is. These moments would be what we call proto-conscious, because they have subjectivity, but they're not the kind of consciousness we have, which is a logical cognitive scene. So he put forward this idea that this separation and self-collapse, or objective reduction, he called it, quantum state reduction due to an objective threshold, would occur due to any superposition. And that something like this must be happening in the brain in a highly organized way, in something like a quantum computer, to give rise to subjective experience. The other key feature was that not only would there be subjective experience, but if the system were coherent enough, the collapse, the choice of over here, wouldn't be random as it is in decoherence or the observer effect, but would be influenced by what he called non-computable Platonic values embedded in the structure of the universe. In other words, he was saying that, going back to Gödel's theorem, there must be some values outside of the system, that would influence this. And I think of this now as kind of resonance with what he called Platonic values of pure form, going back to Plato, but very consistent with what Ervin Laszlo has been talking about, the Akashic record, Teilhard de Chardin with the noosphere, Jung's collective unconscious. There are many, many examples of intrinsic cosmic wisdom embedded in the structure of the universe. And Roger brought this in the fine-scale structure of the universe, and it wielded influence at the instant of collapse, saying, so zooming ahead to where we are now, if you're mindful and are contemplating a decision and don't act rationally, you can be influenced by these Platonic values to choose the right thing, perhaps by resonating with Platonic values embedded in the structure of the universe. So I was reading all this, and I was kind of blown away by it, because the breadth and depth of this book just floored me. And I didn't pretend to understand very much of it. I was kind of skimming the surface. And but Roger uses very, nice cartoons and simple drawings, and gets his complex ideas across beautifully. So I got the basic idea of superposition self-collapse. And he said there must be in the brain some kind of quantum computer that could use this objective reduction. But he didn't know what it was.
Bringing us back to your work.
Exactly.
Now.
So for example, a neuron firing or not firing is much too big to be a quantum state.
Right.
So I remember thinking, oh my goodness, he's got the mechanism for consciousness that I was looking for. And I have the structure, the microtubule, to be the quantum computer that he was looking for. And I figure, what have I got to lose? I wrote him a letter. I sent him a bunch of papers I'd written about microtubules, told him about microtubules, mentioned a book I'd written about microtubules, and mentioned I was going to be in England for a conference in Bristol, actually.
And I'm assuming this is a person who gets stacks of letters from people who feel they have some key to his research.
Exactly. Probably the vast majority totally daft.
Right.
Totally
so
crazy.
How did he actually even find in this massive correspondence your...
I don't know, but he did, and I'm glad he did. And sure enough, I got a letter back. We didn't have email back then, or at least he didn't, or I didn't. I guess I did, but anyway, I got a by post, and he said, yes, this is very interesting, and if you're here such and such a time, why don't you come to Oxford and visit? And so I did. And I found the Mathematical Institute, his office, which was a fairly large room. I would say it was organized in a very cluttered way, or cluttered in a very organized way. He had stacks of papers. This is, everything was hard copy back then. And he does use computers. He came to use computers quite well, but at that time he wasn't. But every table, every chair, every corner of the office was stacked with papers. But he seemed to know where they were, more or less. So he welcomed me in. He was a bit shy. Roger's, he's a very modest man, very, very wonderful guy. And he said, okay, well, tell me about these microtubules. First of all, these are real. They're not molecular, computer models. No, we've done computer models, but they are real. And I brought several books. One was a book about microtubules by Pierre Dustin, and another was a book that I wrote in 1987 called Ultimate Computing, about microtubules processing information. Little did I realize we hadn't scratched the surface of Ultimate yet, but because I didn't even know about quantum computing when I wrote it. But I went through it, and one of the things that really intrigued him was the Fibonacci geometry of the microtubule. So microtubules are made up of proteins called tubulin, which are peanut-shaped proteins, which, if you have enough tubulins in the right conditions, will self-assemble into microtubules, and this is how cells grow and neurons grow and make new connections and so forth. And there are 13 of these chains of protofilaments, and the tubulins form a lattice, which happened to be a hexagonal lattice, and with a skew, so it wasn't symmetric, with a skew, so that if you followed one row of tubulin around the microtubule, you came back on the same protofilament. And there
in a spiral?
In a spiral, actually 3 spirals. There's a 3 start, so if you go around, you come back on the same one, 3 tubulins up, or 3 tubulin monomers up. If you go another way, you come back at 5, and if you go another way, you come back at 8. And then there's others where you have to skip. So if you Dustin in his book had noted that these repeating helical spiral patterns match the Fibonacci series, of where you add 1 and 1 is 2, 2 and 1 is 3, 3 and 2 is 5, 5 and 3 is 8, 8 and 5, 13, 13, 8, 21. And the Fibonacci geometry is found widely in nature, in sunflowers, and
we often call it sacred geometry.
It's a sacred geometry, yes. It's just widely through nature.
Right.
And why that is another question, but microtubules had them also, so that really intrigued him. And he also realized they were the scale where quantum effects could occur. And but proteins are, their ends are polar, they're in water, highly charged, not very conducive to quantum. But what I knew from studying anesthesia and proteins was that inside each protein was a nonpolar region of what's called pi resonance electron clouds. It's like a benzene ring, a phenyl ring, in amino acids, tryptophan, phenylalanine, tyrosine. And oil and water don't mix. So in the middle of proteins and in the middle of lipids and nucleic acids is this nonpolar, quantum-friendly region buried and shielded from the aqueous environment. And in microtubules, it was such, it turns out, we found out later, that we now call it the quantum underground, that the quantum underground in one tubulin would connect to the next one, to the next one, to the next one. So we have these macroscopic helical pathways of quantum-friendly regions. And that, we think, is where the quantum stuff happens that leads to, eventually leads to objective reduction and collapse. So I explained some of this to him, and he mentioned he was going to a conference at Cambridge with Dan Dennett and Pat Churchland and some other people on consciousness who had invited him because he started writing about consciousness. And I said, gosh, that sounds like fun. Good luck with that. So I was headed elsewhere. And 2 weeks later, I was back in London about to fly home, and I had dinner with a friend, and he said, hey, guess what? This friend of mine went to this conference at Cambridge with Dan Dennett, Pat Churchland, and Roger Penrose was talking about you and your microtubule idea. I'm like, oh my gosh. I was really thrilled. Right. So the next thing was that I got invited to a meeting in Sweden that he had been invited to, and he must have recommended me. And it was a wonderful event above the Arctic Circle, or Polar Circle, they call it there. An isolated station without an audience, just speakers, participants. And we got to know each other, and I invited him at that time, and his wife Vanessa, who's wonderful. And we played ping pong and went hiking in the midnight sun and went skiing, did all kinds of fun stuff. And we started to talk about how we might develop, how OR, objective reduction, might actually happen in microtubules. So then he came to Tucson the following spring, and at the first Tucson conference in '94. And then I had a couple weeks off later, a couple months later, and went to Denmark, where it turns out Roger and Vanessa go every year on holiday. And we wound up sharing a house. There was a conference there at the Danish Technical University where I had done my sabbatical. And so they were eager to have him to speak also. So we hung out in this house for a couple of weeks and started to develop our theory and quantify it. And I remember one night I stayed up and did some math just to figure out how many. So he gave me the formula, E equals H over T, and then we had to figure out how this might work in the brain and how many tubulins or how many neurons would be required for one conscious moment at some physiologically relevant moment time scale. And I did the math, and it turned out to be about 100,000 neurons, and I showed it to him at breakfast, and he said, oh, is that good? I said, that's very good, because Francis Crick and Christoph Koch and other people have been talking about 100,000 neurons for a conscious moment. I said, we're in the ballpark. So that was good. But of course, there are many, many other details to be worked out, and mainly how do you avoid decoherence and so forth. But that was the start, and it was funny.
Can I ask you a practical question? Yeah. So this research, so do you feel, we're all talking about a shift in consciousness happening on the planet right now. What role do you think actually being able to define consciousness has in this greater picture of shifting consciousness?
Right. So if we fast forward to today roughly, there are basically two ideas. One is that consciousness emerges from complex computation. It's the old AI, the brain is a computer idea. And according to that, there's, afterlife or connectivity is impossible. It's an emergent phenomena, and there's nothing special. It
dies with the body.
However, there's also, panpsychism and Eastern philosophy, and now the quantum approaches, which suggests that consciousness is intrinsic. And this would include Roger's idea that these collapses, objective reductions, occurring everywhere, and that consciousness is intrinsic and has other features. So although Roger doesn't like to discuss applications and implications of his ideas to what might be considered from his side of the realm somewhat unscientific, even though I think it's becoming more and more true, it does lend itself to that, and it puts consciousness into the universe. And let me make so the individual objective reductions that would be happening here have moments of awareness, but they're not organized. They're kind of like, we call them proto-conscious. They're kind of like, if you go to the symphony, the sounds and tones of an orchestra warming up. They're each doing their own thing. You hear all these tones. It's not music. And then the symphony starts, and you have music. So what the brain does, what the microtubules do, is organize and orchestrate all these individual objective reduction moments into literally music. And I really think that consciousness is more like music than it is like computation. At the brain is more like a quantum orchestra than it is a computer. So yes, I think his approach and our approach is helpful and a scientific lifeline to the kind of things we're hearing here at this conference and that people would like to believe.
Well, I appreciate you taking the time to actually elaborate some of this for us, and would look forward to understanding what this research leads us to in the coming years. So Stuart, thank you for being with us.
Thank you, Betsy. Thanks for having me.